Hello, students. Welcome back to our next topic in our study of science. And this week, we are going to be exploring the topic of nuclear chemistry. Woo, a hot topic. Hot topic. Nuclear chemistry is where it's at this week. And in nuclear chemistry, we're going to be talking about things such as the sun. Ooh, that's a hot topic, man. Oh, yeah, the sun and how the sun utilizes nuclear fusion reactions to power our entire solar system. Yeah, believe it or not. It's nuclear chemistry in action. Next, we'll talk about nuclear bombs. And you'll see some videos, if you haven't already, about the most powerful nuclear bomb ever detonated on planet Earth. It's pretty scary stuff. And speaking of nuclear bombs, Albert Einstein once said, mankind invented the atomic bomb, but no mouse would ever construct a mouse trap. Think about that for a moment as we continue this week and next to discover the incredible energy released from the nucleus of an atom. Nuclear warfare is like the mousetrap for humans that we made ourselves. We could literally annihilate not only our own species, but many other species on the entire planet if we unleashed our entire nuclear arsenal. That would be a bad thing. So take a word of advice from Albert Einstein and think about this famous quote of his. But for now, let's dive into radioactivity. And perhaps you've got that song in your head like I do mine, radioactivity. And I'm not going to be showing you the videos during this video because I don't want to infringe on any copyright issues, if you know what I mean. But I am going to be linking you to a number of other videos that I'm going to be asking you to watch regarding radioactivity, which ties into our topic this week. By the way, do you see this here? We'll get into this later, but this is a radioactive nuclear decay series. It might look like Greek to you, but by the time we're done with this topic, you'll understand what that is saying to us. In fact, we'll go over this nuclear decay series of uranium-238. It's actually cool because it ends in lead, but we'll get to that later on. So you're going to watch a video. By the way, this is the universal symbol for nuclear radiation, and here is an illustration of different types of radioactivity that we will be exploring: alpha, beta, and gamma. These symbols here are going to become familiar to you this week because they are used, these Greek letters are used, these Greek letters, alpha, beta, and gamma, are used in the field of nuclear chemistry. But let's begin in our notes here with what radioactivity is in its most simplest form. Radioactivity is a release. No, not a release of stress, but a release of matter and energy that actually changes the nucleus of an atom. I know. Earlier in the year, we learned about atoms and we learned about the structure of atoms, and that's all important information. But today and this week, we're going to be learning about how that can change and how it can change markedly. So, radioactivity, the simple definition of it is a release of matter and energy that changes the nucleus of an atom. And I've underlined words there for a reason. You might want to underline those words as well in your notes as we plow forward. So, what are the three types of radiation? Again, I'll be linking you to a video to watch, but they are very simply alpha, beta, and gamma. And alpha, beta, and gamma are the first three letters of the Greek alphabet. And so let's talk about these first three types here for a moment. Alpha particles are abbreviated with the Greek letter alpha. And as you write it in your book, it kind of looks like a fish with an open tail. So practice drawing the alpha symbol, which is the first letter of the Greek alphabet. And so, what is an alpha particle? Well, an alpha particle, again, abbreviated by the Greek letter alpha, is made up of four things that come out of the nucleus of an atom. You can see and you can recall that a nucleus of an atom is made out of positively charged protons and neutrally charged neutrons. Protons and neutrons are in the nucleus of an atom. However, here's where things get interesting. It's not that easy because some elements have atoms that are not stable, like me, and they tend to fall apart. We'll get into that later on. But as they fall apart or decompose, those protons and neutrons can undergo changes in location, position, and their mere existence can change. So let's get back to an alpha particle. What is it? You may have guessed already based on the diagram there, but an alpha particle is made up of two positively charged protons and two neutrally charged neutrons. So two protons and two neutrons are essentially what an alpha particle is. Now, if alpha particles are emitted or released or decay from the nucleus of an atom of an element, we can measure the effects of that. In fact, later on this week, I'll show you a Geiger counter, which will measure radiation. But alpha particles released can have an effect on human beings. They can burn your skin, kind of like sunburn. However, alpha particles are very weak, and you can stop alpha particles with a single sheet of paper. So if something were emitting alpha particles, I would be protected just by holding up a sheet of paper, and I would be protected from them. But without that, they could give me a skin burn. Alpha particles also can only travel a short distance of a few centimeters, and that's it. They can't travel long distances. So make sure you know alpha particles, what they're made up of, two protons and two neutrons. They can burn your skin, but you can stop them by a sheet of paper. Let's move on to the next one, which are beta particles. Beta particles are abbreviated by the Greek letter beta, which looks like a fancy bee with a tail at the bottom and an open bottom. So draw the B for beta particles. And you can see what a beta particle is there, but let's talk about it a little bit more before you write that down because it's a little bit more complicated than just that. But again, beta particles looks like a funky bee with a tail, and a beta particle is made up of one negatively charged electron and one positively charged proton that results from the decay of a neutral neutron. That's a mouthful. Take a moment to write that down and then really think about it. A beta particle comes from a single neutron within the nucleus of an atom, but that single neutron breaks apart, its identity changes, and it breaks apart into one electron and one proton. Basically, the neutrons in the nucleus of atoms are made up of an electron and a proton. That's why they are neutrally charged, because a positive and a negative neutralize one another into something that does not have an electrical charge. So here's the deal with beta particles. Beta particles occur from neutron decay, and they are stronger than alpha particles. Beta particles can go right through your bare hand. In fact, I've had beta particles go through me because beta particles are often used in medical procedures in order to take things like bone scans and see your bone density. So I've actually had beta particles go through my body. But beta particles can be stopped. Beta particles can be stopped by several sheets of aluminum foil. So if you have foil aluminum thick enough, you can stop beta particles. So if you don't want to be exposed to beta particles, just wrap yourself up in aluminum foil and you'll be good to go and baked on the grill. It's probably not a good idea to wrap yourself in aluminum foil. But that brings us to the third type of radioactivity, which are gamma rays. Gamma rays are not particles at all, but rather they are electromagnetic rays. And they are symbolized by the Greek letter gamma, which looks like kind of a twisted Y. Kind of a twisted Y. And you can see the gamma here. Looks like a fancy twisted Y. And a gamma ray comes out during the decay of the nucleus of an atom, but it doesn't come out in the form of particles. It comes out in the form of rays. And you may be somewhat familiar with gamma rays if you are familiar with the movie or the old TV series or the comic book, The Hulk. The Incredible Hulk evidently gained his strength from an overdose of gamma radiation. And I've linked the the video link so that you can see the moment in time when Dr. David Banner got irradiated by gamma radiation. But let's just mention a couple more things about gamma rays, and that is once again that gamma rays are an electromagnetic wave. There is no charge, and they're free. There is no charge on for gamma rays. There's no charge. They're free, and they have no mass. They have no mass. And gamma rays, they are a lot stronger than alpha particles or beta particles. Gamma rays can go right through paper, right through your body, even if you're wearing an aluminum foil outfit. They need to be stopped by thick concrete and lead. That's why during the 1950s and 60s, something became popular. They were fallout shelters. Fallout shelters, people started building them in their backyards, and they were lined with concrete and lead to protect what people thought was going to be an inevitable thermonuclear war between the United States and the Soviet Union. And if there had been an all-out nuclear war, our planet would have been bombarded not only by alpha particles and beta particles, but a lot of gamma radiation as well. And people knew even back then that it took thick layers of concrete and lead to stop the flow of gamma rays and protect people on the other side of gamma radiation. What they didn't consider, though, in the 50s was that you really only have a very limited amount of time to be protected by these gamma rays in the fallout shelters. And without protecting the entire surface of planet Earth, all of the continuing food resources would also be annihilated. So, unless you started resorting to cannibalism in your fallout shelter, by the time your food resources were depleted and you came out of your fallout shelter, there would be no life on the surface of planet Earth anymore. And that still remains a theoretical possibility in the future as well, because even now, if the entire planet's nations unleashed our thermonuclear warfare or warheads, it would annihilate just about all life on the surface of planet Earth. But it has become much less an immediate mental burden to us because of the end of the Cold War between the US and the former Soviet Union, and various arms reduction treaties like the START reduction treaty, I forget what it stands for, but back in the 1980s and the 90s, civilized nations saw the foolishness of engaging in a thermonuclear war with one another, and so it has become less on the forefront of our consciousness. But it's probably always a good idea to remember what could happen. So here's a quick summary of the types of radioactivity. An alpha particle is basically helium nucleus when you think about it. A beta particle is kind of like an electron, and a gamma particle is a high energy photon of light. Don't worry about writing that down, because what I'd rather you do is we're going to summarize, create a summary table of the three types of radiation in this way. So here it is: alpha, beta, gamma, alpha particle, beta particle, gamma rays. The atomic mass of an alpha particle is 4. This is going to be important information in the near future. And an alpha particle has a charge, an electrical charge of a positive. Beta particles have an atomic mass of 0. Think about it. You're losing something from the nucleus, gaining something around, but there's a net balance between the two. But beta particles do have a negative charge, and gamma rays aren't particles at all. And so there is no mass and there is no charge, because gamma rays are free. Ba-dum-bump. So we're going to call it quits there for today, and we will continue with our notes tomorrow as we discuss tomorrow nuclear stability. So for now, I'll say bye bye.